Sam Ting and many of the distinguished members of his international research team working together on an extraordinary experiment called the Alpha Magnetic Spectrometer. And I've already been asked, why alpha? Why not something else? So maybe Sam will tell us that. This amazing instrument, as Sam will tell you, is going to be taken to the space station, and there it will carry out measurements of fundamental importance to understanding the origins of the universe. The experiment, in our view, is a model of international cooperation. Sam has even brought together Taiwan, the People's Republic of China, along with 13 other countries and 200 people or so from a total of 31 institutions around the world, in addition to many subcontractors and suppliers from many other nations. But projects of this scale and complexity are not always smooth sailing. George Abbey and I have had the privilege of working with Sam and with former Congressman Nick Lampson on some political issues that arose in connection with the experiment, and we're very pleased to have Congressman Lampson with us today. Thank you, Congressman, for all you have done and continue to do for Johnson Space Center, for NASA, for the U.S. space program. Now, so that Dr. Ting and his team can tell you the amazing story of science and science policy, I will keep his introduction very short, and he will introduce his team. Our physics and astronomy colleagues, of course, know Sam Ting, and they need no introduction at all, but for the benefit of others who are here, I'll say a few words. Sam Ting was born in Michigan. He lived in China and Taiwan. He later obtained his degrees from the University of Michigan in his birthplace town of Ann Arbor. He joined the MIT faculty in 1969, and where he is today, Thomas Dudley Cabot Professor of Physics. Sam is a member of the National Academy of Sciences and is an academician of the Chinese Academy of Sciences and Taiwan's Academia Sinica. He's received many honors, including the 1976 Nobel Prize in Physics, which he shared with Bert Richter for the discovery of a new particle, the J-psi meson, which established the existence of a new kind of quark by the attractive name of charm. Indeed, charm is an attribute that is appropriate for Sam Ting, and that said, though, one thing those who know Sam might say about him is that no matter how high the obstacles may be, he finds a way across or through. That tale of the AMS illustrates the point very well, so please, everyone, welcome Sam Ting and his colleagues.
I'm honored to be here. I'm particularly pleased that my distinguished colleagues have the chance to come here. Coming with me, there is Manuel Aguilar, who is, I think, the only particle physics member of the Royal Spanish Academy of Sciences. The Royal Spanish Academy of Sciences is different from the U.S. Academy of Sciences in the sense only when one passed away, you select a new one. And so they are called immortals. And he's also a very distinguished physicist in his own right. And we've known each other, be friends for many, many years. He's currently also the head of the research division in the Spanish National Laboratory in Madrid, known as CMAT. Next to him is Professor Maurice Bourquin, and former president of University of Geneva, and chairman of the board of directors at the European Center for Nuclear Research, known as CERN. And Maurice also is a very distinguished physicist, worked at CERN and also for many years at Fermi National Laboratory. And next to him is Arturo Menchaca, a very close friend, who is the president of the Mexican Academy of Sciences, and he worked very closely with our colleagues in France, in Grenoble, also worked closely with Manuel Aguilar in Spain, and did very important work in one of our detectors. And next is Roberto Battiston. And Roberto is the chairman of a committee on astroparticle physics in Italy. As such, make decisions on trend of research in Italy on the directions of astroparticle physics. He himself is a very distinguished physicist in his own right, and worked at the proton colliders in 1983, and then subsequently worked as SLAC, and then we worked together in electron-positron colliders, and also is now the deputy spokesman for the AMS experiment, and not only in scientific policy in physics, but also is a very gifted person in instrumentation. Made very many major contributions on instruments in particle physics. And Professor Lee is for many years at the Institute for Advanced Study at Princeton, and then worked at Stony Brook, and returned to Taiwan. Is in charge of most of the high energy physics and astrophysics program in Taiwan. Knows a lot about physics. Basically coordinate all the efforts we have in China and in Taiwan. And last but not least, let me introduce Dr. Susan Ting, my wife, and from MIT. And she always makes sure I say the right thing at the right place. So what I would do today is to give you a very simple description of the experiment which my collaborators and I are doing on the International Space Station. The International Space Station from here to here is 109 meters, from here to here is 80 meters, and therefore it's the size of 3 football fields, at a cost about $100 billion. And this experiment is the only major science experiment on the space station. The German physicist and philosopher Christopher Lichtenberg wrote in his diary 200 years ago, to invent a remedy against toothache, which would take it away in a moment, might be more valuable than to discover another planet. But I do not know how to start a diary of this year with a more important topic than the news of a new planet. It was the planet Uranus, discovered in 1781, and which was recently investigated more closely by the Voyager spacecraft. Even at that time, one was confronted with a problem which is as important today as 200 years ago. Should we build satellites to explore the universe and accelerators to investigate the microcosm at a time when burning problems like unemployment, healthcare issues, environment hazards trouble our society. Here is the diagram on physics. This is the pure research in 1900, this is 1930s, and this is today. Physics is a question of dimensions. This is going to large dimension, this is going to small dimension. 100 years ago, we studied thermodynamics, mechanics, optics, leading to today's television, aircraft, steam engines. In 1930s, so-called frontier physics, solid-state physics, quantum mechanics, leading to superconductivity, laser, communication, microchips. In 40s, the frontier physics is nuclear physics, leading to reactors. For larger distances, in 1930s, we studied cosmic radiation and the sun. Now is used for navigation and timekeeping. So this pyramid which has grown with new application increases height, where fundamental research continue widen its basis. The role of basic research implies it finds itself at the outermost corner of the pyramid and hence is sometimes blamed for being too far away from daily life. Only after some time, when application grows and public is more acquainted with the strange new phenomena, they seem to be more real. The issue of fundamental science the issue of fundamental science and International Space Station can be very simply visualized. There are two kinds of cosmic ray traveling through space. The one doesn't carry charge, called light rays, and called neutrinos. Light rays have been measured, for example, by Hubble telescope for the last 50 years. Almost all our understanding about cosmos has been from study of light rays. But then there's, beside light rays, the particles carry their charged cosmic rays, which is an unexplored region in science. Using a magnetic spectrometer on the space station is the only way to measure very high energy charged cosmic rays. In other words, there are two kinds of cosmic rays. One has been measured by everyone, and this is the first time one enters into a new region. I want to acknowledge the importance of using space station as a unique science base was recognized by scientific, space, and political leaders in the United States, including Dr. Neil Lane, Mr. Abbey, Ms. Israel Gowan, Senator Bill Nelson, K. Bailey Hutchinson, Congressman Joe Barton, Rob Hall, Chet Edwards, Nick Lamson, and many others. This is not a NASA experiment. It is a DOE-sponsored international collaboration. DOE, Department of Energy, has the wisdom to select some of the best physicists, members of the National Academy of Sciences, and Nobel laureates to review this experiment. It is because of this the scientific value was never subject to doubt. It was also reviewed in Switzerland, in Italy, in Germany, in Finland, in many other countries, as well as by the European Space Agency. It is a large international collaboration involving 16 countries, 60 institutes, and 600 physicists. Together with Mr. Neil Lane, we have realized we have been together for 5,000 days. And this is not a cheap experiment, perhaps because of my poor management style, and well, close to $2 billion has been spent, 2.5, but most of them has come from outside United States, from Finland, from Denmark, from Holland, from France, from Spain, from Portugal, Italy, Switzerland, Romania, Germany, Russia, Korea, China, and Taiwan. It is based on NASA's commitment to deploy this experiment on the space station. So the scientists in the experiment are mostly European, have worked together for many years. And here's my small summary of my involvement in international collaboration. When I first started doing experiment in Germany, my collaborator consists of 10 physicists. And the experiment cost $10,000. Now, there are close to 600 physicists and more than $2 billion. This experiment has always been very strongly supported by the United States Department of Energy. Here is the communication from Ray Orbach, Undersecretary for Science, to the then administrator, mentioning AMS as important mission for the Department of Energy. This is the latest letter I received from the head of the European Space Agency, Monsieur Jean-Jacques Dordain, 3rd of February. He said, I confirm that I grant the highest priority for AMS of O2, providing access to the test center. From the European Organization for Nuclear Research, CERN, there's Dr. Steve Myers, Director of Accelerator and Technology, who mentioned there is a decision from the director level to give maximum possible amount of help to AMS. The question is, why so many people support you? So let me share with you a few examples of our past work using accelerators. The first example is the discovery of nuclear antimatter in New York Times, June 1465, which says, physicists produce antimatter particle in complex form. The second contribution we made was discovery of new form of matter in New York Times, November 1774. New and surprising type of atomic particles found. The third example is the discovery of gluons in the New York Times, September 2nd, 1979, the detecting of elusive gluon exciting scientists. In nature, we know there are 3 types of forces. Gravitation. Gravitation was discovered in 1610 by Galileo, but even today, we do not know what transmits gravitational force. The collapsing of stars is called electroweak force. It's carried by these 3 particles, has all been discovered. Transmission of nuclear force is carried by gluon. So this is somewhat of an important discovery. The confirmation of how stars decay is called electroweak theory. And if this occurs, when you measure electron-positron, you have a characteristic behavior. And so electroweak interference was confirmed. And that's a very important contribution. Most of my collaborators worked together for 20 years in the electron-positron collider at CERN, called L3, And this is not a space experiment. It weighs 10,000 tons. It has a height of 6-story building. And Susan and I live in here. This is the front page of Scientific American. This experiment published 300 papers. It's large. But in physics, the basic idea is always very simple. And so the results can be summarized in a few words. That is, in universe, there are only 3 types of electrons. The electrons we're familiar with, the electrons from space, the electrons in the nucleus. There are only 6 types of quarks. But the most important, the most curious thing is the electron and quark has no size. We use electricity all the time, but we seem to be never been able to measure its size. The radius of the electron and the quark is less than 10 to the minus 17 centimeter. That is a very, very, very small number. Less than is not equal to. The results are in excellent agreement with the electroweak theory of Weinberg, Glashow, and Salam. That, of course, is unfortunate. When the experiment agree with the theory, you learn nothing. It's when the experiment confront the theory, you learn something new. So the collaboration's record is the main reason why we receive so strong support. I think that also is the reason Mr. Abbey, Mr. Neil Lin, Mr. Israel Gabon, and others support us. I should also like to mention many theoretical physicists, Alan Guth, Steve Weinberg, and so forth, have continuous interest in AMS, and they have contributed greatly in the formation of our analysis framework. The experiment itself is a very simple device. Once you realize particles are defined by their mass, charge, and energy. So the first thing measures the electron. The second detector measures mass, charge, and energy. Then you have a magnet with a detector. You measure mass, the sign of the charge, and energy. And this detector measures mass, charge, and energy. And this detector in the bottom measures electrons and gamma rays. There has never been a superconducting magnet in space due to the extremely difficult engineering and technical issues. The AMS superconducting magnet has the following properties. First is there's no ion, and therefore to reduce the weight. The second, no field, all the magnetic field are confined inside the magnet, and so it's safe for the astronauts to walk nearby. And third is there no influence from Earth's magnetic field. A magnet, of course, will always rotate in a magnetic field. And this is one of the main reasons for 40 years nobody were able to put a magnet in space, because soon your space shuttle will lose control. And we have managed to design a magnet with 2 closed loops, and so the field basically is only inside. Outside this cancels this cancels this, and this one cancels this. Therefore it's totally stable. And looking from outside, it's just like a stone, and there's no field. All the fields are inside. This is a major collaboration from Switzerland, United States, Spain, and Russia. It carries 2,500 liters of helium at 1.8 degrees above absolute zero. For nearly everything, we built 2, and 2 magnets were built, 1 for space qualification, and this was done in Italy and Germany. And as Professor Battistone was mentioning, special laboratory has been set up by him in Italy for this purpose. Next detector is called transition radiation detector. It uses the fact when an electron travels through a foil, it emits radiation. If you have a tube, absorb this radiation, and you know an electron has gone through. Only electron has this property. And so this is the detector in the installation. Now, this is easier said than done. The detector is 3 meters by 3 meters, and it consists of 5,000 tubes, 2 meters in length, centered to 100 microns. Once you seal a tube, you do not know the wire is centered or not. So what we have done is to build 10,000 and assume each one is a patient. We let it go through a CT machine. And then we choose the ones that center to 100 microns. It is from this we realize how expensive it is to go to hospitals. And under the leadership of Roberto Battistone, we built a silicon detector, and there are 8 planes, 200,000 channels. That's a major international collaboration in its own right. With a resolution of 10 microns, you can simultaneously measure all the nuclei. And this is how the detector was put together. And then, involving with Mexico, with France, with Italy, and under the leadership of Manuel Aguilar, with Spain, it's a ring image Cerenkov counter, and this is a detector which uses the fact a particle goes through the radiator, emits light. The angle of the light is a measurement of velocity. The intensity of light is a measurement of charge. To do it precisely, we have 10,000 photodetectors inside. On the bottom is a collaboration between the People's Republic of China, France, and Italy. It is a detector consists of 10,000 fibers, 1 millimeter in diameter, sandwiched in 1,200 pounds of lead. So an electron goes through, it generates a shower. So you can measure electrons. So the detector was assembled, took it apart, reassembled, and then a few days ago, from the 4th to the 8th of February, we put this detector in this large accelerator. This is a CERN, and you have particles go from a smaller accelerator, gradually go to the large accelerator. And so this is called super proton synchrotron, 7 kilometers in circumference. You produce a ring of particles, a beam for AMS, and they also occasionally produce particles called neutrinos, which travels 1,000 kilometers to Rome, and you do neutrino physics. But from the 4th to the 8th, the entire complex was devoted to this experiment. And so this is the AMS in the test beam. And it shows the strength of this detector. At 400 billion electron volt, you can measure the velocity to an accuracy at the speed of light to an accuracy of 1 part in 1,000. When an electron of 180 billion electron volt, 250 billion electron volt, 290 billion electron volts go into the detector, you can measure them separately. So you can measure the energy. And you measure the coordinate to an accuracy of 10 microns. It is because of this accuracy, people often refer this as the Hubble telescope for charged particles. I think even in accelerators, you hardly can find a detector with this precision. And so this is the 12th of February, and this is the detector on a huge truck left CERN on the way to the European Space Agency. And I'm told it arrived about 5 hours ago in Holland. And so we had 6 astronauts. I noticed most of them are here. And they will take us safely to space. This is not a cheap experiment. And this is a cartoon that we have just decided to launch money directly into space is cheaper. Probably correct. And the question is, what do you learn? And one of the things you learn is you can measure, beside charged particles, you can measure light rays. Measure light rays in a special region from ground-based telescopes to space telescopes. And one thing you can start study is pulsars in the Milky Way. Pulsars are neutron stars sending radiation in a periodic way, currently measured to millisecond accuracy. Pulsars emit radio, visible, and gamma rays. Currently, the energy is measured to 1 billion electron volt. AMS will measure to microsecond period energy measured to 1 trillion electron volt, namely a factor of 1,000 improvement in time and energy. Improvement in a factor 2, 3 is not important. Improvement of 1,000, you enter into a new region. Another physics example is the question of dark matter. We know 90% of the universe is not observable. Because you cannot see it, you call it dark matter. Nobody knows what dark matter is. The collision of dark matter can produce excessive positrons. And so the current data measured to the blue line shows it's different from what you expected. But these are only 1 or 2 signals. We can make an ultimate accurate measurement and to understand where the 90% of the universe come from. Another physics example is the search for the existence of antimatter in the universe. The Big Bang origin of the universe requires matter and antimatter to be equally abundant at the very hot beginning. Because before the Big Bang, it is vacuum. So at the very beginning, if you have an electron, you must have a positron. You have a matter, you must have antimatter. Otherwise, you will never have come from a vacuum. So now the universe is 15 billion years old, and we have Rice University, we have all of us, and the question is, if it indeed come from a Big Bang, where is the other half? And this is one of the main purpose of AMS. The existence of antimatter was proposed by the great physicist Paul Dirac, received the Nobel Prize in 1933. He realized in the description of relativity, in the description of quantum mechanics, mass comes always in square, meaning can be m times m, can be minus m times minus m. And he asked, what is minus m? And leading to the theory of antimatter. So for a real intelligent person, getting a Nobel Prize is quite easy. Just to figure out what's that. What we can do is to improve, to look for antihelium to helium from the existing limit by a factor of 1,000,000. Namely, look to the age of the observable universe. When you improve by factor 2 or 3, you normally don't learn anything. A factor million, you enter into a new domain. The cosmos is the ultimate laboratory. Cosmic rays can be observed at an energy higher than any accelerator. The issue of antimatter in the universe and the origin of dark matter probes the foundations of modern physics. But the most exciting objective of AMS is to probe the unknown, to search for phenomena which exist in nature that we have not yet imagined nor had the tool to discover. So let me explain to you what I meant. This is the major discovery of physics in the last 50 years. When I first started doing experiments, the highest energy accelerator was at Geneva called proton synchrotron. The justification for its construction was to study nuclear force. What was discovered was the forces in the collapsing of stars. In the United States, a similar accelerator was built also to study nuclear force. What was discovered was two kinds of neutrino, breakdown of fundamental symmetry, new form of matter. Fermi National Laboratory was built in the 70s. The original purpose to study neutrino physics. What was discovered was the fifth and sixth type of quarks. Stanford Linear Accelerator was built for electron-positron collision, originally to study property of electricity. What was discovered is quarks inside the proton, the new form of particle, and third electron. In Hamburg, the largest accelerator was built in the 1980s. Originally was to look for the sixth quark. What was discovered was the gluon jet. The large underground experiment in Japan originally was for the lifetime of proton. What was discovered, actually neutrino has mass. Hubble telescope. The original purpose was galactic survey. What was discovered was the curvature of the universe in a four-dimensional space is flat, and there exists a new form of energy called dark energy. So I'm wasting some of your time to mention how important it is for AMS to look for dark matter, antimatter, but what we really will discover, nobody would know. The reason is very simple. Experts' opinion is based on existing knowledge. The advancement of physics is to destroy existing knowledge. So you cannot predict the future. So let me comment on key to large international physics collaborations. Let me summarize on 4 points. The most important point is a physics idea. Physicists from different countries are motivated to work together because they find the experiment is interesting and important. The second important thing is of giving credit to young physicists and students. International collaboration often lasts for more than 10 years. Today's experiment consumes a major part of professional life of a physicist. To sustain a collaboration, it is of utmost importance to recognize and support outstanding young physicists. Besides some of my collaborators here, I've been privileged to work with Harvey Newman, who is a professor of Caltech, Stu Smith, professor of Princeton, Susan Cooper, professor of Oxford, Marian White, is director of Accelerator Laboratory in Oregon, Becker, Weislauch, and Fisher of MIT, Chen and Zhou of Michigan, Masaki Fukushima of University of Tokyo, and so forth. The third important thing is to obtain financial support from participating in countries. a thorough review by first-class physicists are of great importance. The track record of a collaboration, of course, has a major impact on the review panel. And finally, the importance of ensuring each individual institution keep their identity and have their contributions properly recognized. But the most important thing I want to summarize for you, you may want to ask, after spending 5,000 days, $2 billion, and what you're going to, what is the use of your discovery? To estimate the importance of discovery is very difficult. Let me submit you 3 examples. Lord Rutherford, Nobel laureate, said the energy produced by breakdown of atom is a very poor kind of thing. Anyone who expects a source of power from transformation of these atoms is talking moonshine. Lee DeForest, a very famous US physicist, said, where theoretically and technically television may be feasible, commercially and financially, I consider it an impossibility, a development of which we need waste little time dreaming. Lord Kelvin, the foundation of modern thermodynamics and the person who first figured out how to lay the transatlantic cable, said X-rays are hoax. So you would not want to ask my collaborators to say what we are doing, okay, will contribute. Thank you. I please ask Professor Aguilar to make a contribution, on the Spanish contribution. How do I put it? Oh, I think it's up. Oh, it's up.
Can I have the pointer?
Pointers are there.
Okay, perfect. The other way around. I know. Good evening. I'm really very honored to be here today, and I am going to briefly describe what has been the contribution of Spain to the AMS project. This contribution has been organized through CIEMAT, which is my institute, which is the leading institute in Spain devoted to energy, environment, and basic research in particle and astroparticle physics. It's located in Madrid and is a public research organization. There is another public research organization working in AMS, collaborating with us, which is the Institute of Astrophysics in the Canary Islands. This institute hosts the largest set of facilities, telescopes, in the Northern Hemisphere. Our contribution to AMS has been focused in 2 main items. The superconducting magnet, which has been briefly described by Professor Ting, and the Cerenkov detector. I will give you some more details on what is our precise contribution to these 2 things. In order to fulfill our responsibilities, we had either to upgrade some instrumentation, for instance, in the Institute of Astrophysics in the Canary Islands, or build new facilities. For instance, in my institute, we had to build a brand new clean room, class 10,000, to characterize some of the photosensors for the rich detector and do the assembly under adequate conditions. More important than that is that we have been able to establish relevant collaborations with other public research institutions and with industry. For instance, we collaborated with the Ministry of Public Works, an institute which has a lot of expertise in magnet construction and superconductivity technologies. We also use some of the advanced space test facilities at the Ministry of Defense to space qualify our instruments. And what was more important, we established a very close collaboration with several industries, in particular with CRISA, which is a leading European company working in the electronics sector. In particular, this company has built the electronics for the docking system of the European ATV to the International Space Station. On the cryomagnet, our main duty was to build the cryomagnet avionics. This is the electronic system which is going to fulfill three purposes. On one side, is going to charge the magnet, and once the magnet is charged, it requires no additional power. We have already tested in the lab that the magnet could live for almost 100 years. The decay of the field is of the order of 1% per year. Moreover, the operation of a cryomagnet in space is a very delicate matter. You have to control the behavior of the coils and also the cryogenics, and then you have to design, build, and test advanced telemetry. Moreover, we have to self-protect the magnet in case that there is a transition from the superconductivity state to the resistivity state, or there is a loss in communication, or a failure in power. This is one of the elements, the one which is responsible for charging the magnet. Here are some of the the telemetry boards. There are some of the boards which are standard. They control something like 200 sensors, but there are some of the modules which are really very precise. They have to measure temperature difference of the order of 1000 degree Kelvin with a precision of 100 microkelvins. We build, as it normally we do for this kind of experiments, two models. One was the engineering model, in which we check the functionality and the performance of the system, and then a flight model. This was extensively tested and qualified for a space operation at the company CRISA in Madrid, and also for the vibration test we do it at the Ministry of Defense. And this is a picture in which the avionics system is already attached to the unique support structure of the AMS experiment, which is the main structural component. The other commitment that we had with AMS was to take care of the design, construction, testing, qualification of one very important detector, and this is a project that we did in collaboration with Italy, with France, with Mexico, and with Portugal. The purpose of this detector is twofold. We have to make a precise measurement of the velocity of charged particles, and by precise I mean to measure the velocity with a precision of 1 per thousand. And also we want to measure the charge of the particles. Professor Ting has already mentioned what is the physics principle of this detector, which is the Cerenkov effect. When a charged particle crosses a radiator and the velocity of the charged particle is larger than the velocity of the particle of the light in the radiator, it emits a light cone. And by measuring the diameter of the light cone, we can obtain a precise measurement of the velocity. By measuring the density of points, the density of photons along the circumference, we can measure the electric charge square. So there are three main components of a detector of this kind. One, you have to select properly a radiator. Then you have to build a conical reflector to maximize the collection of photons. And then you have to build a detector plane to measure precisely the energy of the photons. The concept of the performance of this detector has been extensively checked, both using cosmic rays and also using particles produced at the CERN accelerators. And we have a proof that we are going to be able to distinguish and to reconstruct precisely all the cosmic nuclei until cobalt. This is a view of the radiator that we assemble in this clean room that I mentioned at the beginning. We are using two kinds of radiator for purpose that it is not appropriate to discuss it here. This is a photosensor plane, which is made of 680 photomultiplier. Each photomultiplier has 16 pixels, so all in all we have close to 11,000 photosensors. This is a view of the assembly of the readout electronics that we did also at CIEMAT. These electronics were designed by us and built by the company CRISA. Here is a picture of the assembly process of the reflector. Already here is assembled on top of the photosensor plane. And this is a view of the process of assembling the protection against micrometeorites. All these components, as it was the case for the cryomagnet avionics, have been extensively tested in various facilities. For instance, here we did a vibration test of the mirror, of the photosensor plane, the bridge shieldings at the Ministry of Defense. All the electronics components, low voltage, high voltage, readout, were tested for vibration, thermal cycling, electromagnetic interference test. And then we went to CERN with these various components, and we did the final integration at CERN in a clean room, which we built ex professor for this purpose. Then, when the enriched detector was put together with the calorimeter and other components of the system, we did extensive tests, extensive cosmic ray data acquisition and data analysis, an operation that we repeated several times, in particular when the system was fully assembled at the beginning of the year. What we have learned is that our detector is performing according to the technical specifications. We are able to measure the velocity with a precision per thousand, and we are able to measure the charge, and the charge and resolution is a fraction of 0.2. To conclude, I will have to say that AMS is the only large-scale Spanish involvement in science on the ISS. And for this particular reason, we have received in the last 14 or 15 years the strongest support from the Spanish authorities and the Spanish funding agencies. Thank you for your attention.
Okay, it's really a pleasure for me to be here today to present the Italian contribution to AMS in the framework of the particle physics in space on the ISS program performed by the Italian groups involved in this experiment. Okay. As Professor Ting has mentioned at the beginning, space is the ultimate laboratory for fundamental physics. By looking at different scales and different objects with different instrumentation, we can learn a number of things which are at the basis of our understanding about science. In particular, looking back to the very first instant after the Big Bang, we are studying phenomena which are very strongly related to the existence or the disappearance of antimatter, which is one of the main purposes of the AMS experiment. And the scales which can be reached in looking to the universe are unreachable by most powerful accelerator. In this chart, you can see the energy which can be reached by the large accelerator already built, like LEP, or the one which is now starting at CERN LAC, or the future one, are in a scale which, comparing to the scale of the unification of all forces at the Big Bang first moment, is still fairly small. It will be impossible to reach higher scale than that, and the only way to study fundamental phenomena like the disappearance of the antimatter, proton decay, strings, and so on, is to look to the signal coming from the depth of the universe. And indeed, looking to cosmos and to radiation from the depth of the cosmos was instrumental for the birth of particle physics between 1910, when the cosmic ray was discovered, and 1955, where the first accelerator were operational and started the so-called revolution, which got to the Standard Model, which allowed the understanding of many different particles. And today, the discovery of the mass of the neutrino and the possible hint of dark matter observed in a cosmic ray measured from space are suggesting that cosmic radiation is showing again its physics potential. So we are back to 1 century ago, when particles coming from sky, from the cosmos, were giving fundamental information about physics. Indeed, what we know today of the standard model of cosmology is that we have a radiation at the 4% level. We have dark matter, 23% of it is making our universe, but we don't know nothing about it. Dark energy, 76% of it, which we know even less. Antimatter apparently has disappeared. So we are living in a very exciting times, because never before we were so knowingly ignorant about nature. We only understand about 4% of the total. The remaining 96% we don't understand. We don't understand why the antimatter has disappeared. But we know that these kind of questions are open in front of us to be answered. How to study this fundamental question using radiation from space? You build detectors which are operational in space, like the Fermi Observatory, like the AMS and other. You build balloons, or you build detectors located in the various places on the Earth. But obviously, when you are below the atmospheres, the particles which are going to measure are secondaries of the primary particle coming from the depth of the universe. So the information you can gather is much less accurate. So in order to precisely study the cosmic radiation and making precision measurement, it is necessary to go to space. This is why INFN, which is the Institute for Nuclear Physics in Italy, which is consisting of about 1,900 people and 2,500 associate scientists, and operating for national laboratories, 20 sections and 11 associated groups, with a budget of about 280 million a year, euros, has decided long ago to set up a specific group devoted to astroparticle physics, which is investing his own resources and time to organize the participation of Italian scientists to this field of studying the radiation coming from the depth of the universe. We have in this group 6 lines, and one of these is specifically cosmic ray by space experiment, and there are about 850 people working on this subject. This is why Italy has participated to AMS since the very beginning, with a very strong and qualified participation. We indeed were among the people which, together with Sam Ting, proposed the first concept of antimatter spectrometer in space. At that time was based on permanent magnet. In 1994 was built in record time, and in 1998 was flown on STS-91. And this is one of the pictures of that successful mission. In Italy, AMS is supported by 2 institutions, INFN, which I mentioned before, and the Italian Space Agency. And the 2 are working together since now 15 years, supporting this experiment as the largest scientific participation to the International Space Station in Italy. And we are about 60 scientists and engineers, 6 universities, 5 sections, and many other support from the major laboratories of INFN all through Italy. And this is an example of collaboration between the Space Agency and a strong community of scientists which was not before involved in space experimentation. And this is similar to what DOE and NASA did in this country. And this is the way to proceed to progress in this field in space. As Sam has mentioned, AMS is like a gigantic camera to identify particles by particles, the nature of the particle coming from cosmic radiation. At high energy, in a very short time, we can tell the difference between an electron and a proton, an ion and a positron, antiproton, and maybe even anti-helium, which will be form of antimatter, just by reading the various detectors which make the magnetic spectrometer. And the different detector tells you about the velocity, the energy, the sign of the charge of these particles, and by putting together this information, you can really take a picture ID of each particle one by one. And all of that in a very short time at very high rate. More than 2,000 times a second is the rate of acquisition of those particles, and we can measure position to a precision of 10 micron, which is a tenth of a human hair, and 150 picosecond in time resolution, which is a tenth of a billionth of a second. AMS is composed by various subdetectors, and Italy is participating or coordinating most of these activities. As I mentioned before, one of the important contributions together with Switzerland and other countries is the construction of the AMS silicon tracker. Is 8 layers of very special silicon detectors organized in a way they can provide information about what the particle is passing through with an accuracy of 10 microns. And by measuring repeatedly the trajectory of the particle through the spectrometer, you can tell when the particle bends to the left and when the particle bends to the right. And this bending in the magnetic field by the different particles tells you about the charge, meaning tells you matter from antimatter. So this is an essential part of the measurement, which is the basic science AMS is looking for, detecting various forms of antimatter, possibly the nuclear antimatter, which has never been seen before in space. This is a major effort which has taken about 50 engineers, 3 years to complete the detector. And the interesting point is that this has been built actually inside universities, in specially organized laboratories. And some of this technology eventually was spun off to companies which started exactly using this technology to build new detectors. As an example, the technology of AMS has been used to build the GLAST Fermi detector, which is now one of the NASA flagships in space. And this is silicon tracker integration pictures. You can see the detector being installed inside the superconducting magnet, various phases of the installation of the cabling. You can also appreciate the size of this detector by comparing this to the people working at that. This is really a very large acceptance detector, not by chance called the Hubble Space Telescope of cosmic rays. One of the important detectors which Italy has built is also the time of flight system, which measures precisely the velocity of particles and give the time they are traversing the magnet. And this is given at high rate with the precision timing, so basically trigger the entire experiment to acquire the data for the various subdetectors. So it's playing a role not only as velocity measurement, but also as a trigger of the experiment. As mentioned before by Manuel, Italy has participated to the construction and testing and development of the ring imaging detector, which is again a detector which is used to measure the velocity of the particles, which a precision of 1 in 1,000. This is a photograph of it. And finally, we coordinated the construction of the detector on the bottom. The ECAL is a heavy combined mixture of lead and fibers, so at the same time is as heavy as lead to get to stop the particle and measure the energy, and as transparent are fiber, so to collect the light, which tells you how much energy the particle had. and this is located in the very bottom of the experiment. And this is a photograph of the integrated assembly of the ECAL, and with some demonstration of the accuracy in energy and angular resolution. Now, in order to build AMS, we had to develop very major facilities all through Italy to test and qualify the electronics, to operate commercial electronics to make radiation hard for space application through various accelerators we have in Italy, or to learn how to qualify for vibration, shocks, thermal and thermovacuum properties, and EMI properties, the various subdetectors. These laboratories has measured and qualified the AMS electronics and subsystem for about 3,000 hours over the last 2 years, meaning basically working overnight. This is just one example of a qualification testing of the time-of-flight system. This is actual flight hardware. Why I show that is because behind this laboratory there are dozens of students, postdoc thesis, training courses, which has allowed a generation of engineers and physicists to be trained in this field thanks to this experiment. And this is the way university doing fundamental research can train a new generation of scientists and engineers doing the best experiment and the best science which is possible for a space application. So as a conclusion, Italy is a major partner in the construction of the Italian space station. AMS has received the highest priority for the Italian government over the last 15 years, and there are a total of 14 universities, national laboratories, and aerospace companies participate in the construction of this experiment. And we really look forward, and thanks everybody in this room for the support they gave us for all those years. Thank you so much.
So, good evening. I'm very pleased to tell you very briefly what is the Swiss participation in this project. I'm very happy to see many people that I know, in particular the crew of STS-134 in this room. I will briefly tell you that in our small country, Switzerland, you see the outline of the country here, two main academic institutions have participated in AMS since the very beginning. That is the University of Geneva in the French-speaking of Switzerland, and the Eidgenössische Technische Hochschule in the German-speaking part, the Swiss Institute of Technology in Zurich. And in green, you see that a certain number of companies specialized in space, for example, like Contraves, have participated in the construction of the part of AMS for which we are responsible in Switzerland. But let me tell you very briefly why we have decided to participate in this project. We have in Switzerland a very strong accelerator particle physics community, and it is of course somewhat linked to the fact that CERN, the European Organization for Nuclear Research, has its seat in Geneva. We have a lot of expertise and trained staff on the detector design and construction in our Swiss academic institutions. And as I said, we have available in Switzerland a certain number of companies specializing in activities which are useful for an experiment like AMS. So when the opportunity arose in 1994 here in Houston to join AMS in a new field, which you've heard we call now particle astrophysics, this was a very exciting time for us. Particle astrophysics now is essentially the study of the most energetic phenomena in the universe, and also what is called particle physics, not using accelerators. We were, of course, very excited to join this collaboration, and we had already at that time a long history and successful history of collaboration with Professor Ting. Now came the question of funding, how we would fund the Swiss participation in this project. Well, Switzerland, being a small country, has no space agency. It has an office which does coordination with the European Space Agency, a contributor, in fact, to the construction of the ISS, but not directly to other space agencies like NASA. So AMS was selected by the Swiss National Science Foundation following a peer review process, and we have received since that time yearly grants to support the project as basic science. So it is, AMS is considered to be basic science in Switzerland. Now the infrastructure to do the construction of the detectors in Switzerland has been supported by the University of Geneva and by Zurich through the political authorities, State of Geneva and the Swiss Confederation. So with this support, we have been able to contribute essentially, and I will single out two aspects: contribution to the superconducting magnet and to the silicon tracking detector, the detector which tracks the cosmic rays and allows to measure their characteristics. In Zurich, they have from the very beginning coordinated the development of the cryomagnet, and you see here the inside of this magnet, which essentially consists of 14 coils in a so-called magic ring configuration. And in designing this magnet, one realized immediately that one had to develop new technologies in order for this to be successful, using liquid helium, superfluid helium in space. So one had to develop, for example, in Switzerland, the superconducting wire with which the coils are made. And one found a design by using very thin niobium titanium wires in a copper matrix surrounded by very pure aluminum. And this is the design which now is a successful design, allowing to keep the magnet working without difficulties. A second example is the construction of this very large vessel. This is the vessel holding the liquid helium in AMS. It's a large diameter vessel with a very thin thickness. Now, as far as the University of Geneva is concerned, we have participated in the design and the construction of the silicon microstrip detector. You see here an example of the kind of labs, clean rooms we had to build in order to do this work. And you'll see an example of the students and the engineers which have been trained in doing these activities. You see here an example of the elements which are built from the silicon sensors and then assembled in those planes, where the support is a very extraordinary material built by one of those space companies in Switzerland. And the result is that we have built 8 of those space-qualified planes with the resolution expected. You've heard already that the resolution is special resolution is 10 micrometer, and those detectors can also identify the various nuclei and hopefully anti-nuclei if we discover anti-nuclei in space. I'll show you now a few pictures of the construction of this silicon tracker. You see here 3 double planes of silicon which are assembled in a carbon fiber structure. And you see a picture from the top where you see the silicon detectors, the front-end electronics, the cables taking the signals to the outer electronics built in Taiwan, and you will hear a little while how those modules were built in Taiwan. This is a top plane of a larger dimension. And these are pictures of the installation of the inner part of the silicon tracker into the magnet at CERN. So this was assembled at the University of Geneva, transported to CERN, where in the clean room that the collaboration has built, we have put things together. And you see here two pictures of the outer planes being installed into the complete detector. So I stop here by saying that for 15 years we have been part of this project. This has been a major national effort supported by our funding agency supporting basic science, Swiss National Science Foundation. And we are, of course, looking forward for the rest of the work to continue and the results that we are expecting. Thank you very much.
Good evening. I'm glad to report to you the participation of China and Taiwan in AMS. Aside from the Chinese Academy, there are 4 universities: Shandong University from Shandong Province, Southeastern University from Jiangsu Province, Shanghai Jiao Tong University from Shanghai City, and Sun Yat-sen University from Guangzhou. They participate in AMS. And you notice that these 4 provinces are the most affluent provinces in China. So they receive not only strong support from the central government, but they also receive very strong support from the local government. From Taiwan, we have Academia Sinica, which is the leading research institution directly under the presidential office. We have Zhongshan Institute of Science and Technology, which is the research arm of the defense. We have National Space Organization, which is a space agency of Taiwan. We have AIDG, which used to be one institute in the Zhongshan Institute. It builds fighter plane for Taiwan now. And we have 3 national universities participating in AMS. You notice that the personnel from Zhongshan Institute, from National Space Organization, and from AIDG are forbidden to visit China. So it's unusual that we can collaborate with China under AMS project. Professor Roberto Batistone mentioned about our first flight in 1998 using a permanent magnet. And this permanent magnet was built in China, in Chinese Academy of Science. And this magnet is made up from nearly 10,000 pieces. Each piece, the magnetization has to be carefully aligned and glued together. So in order to produce a strong uniform magnetic field inside this chamber, about 1 meter in diameter, however, outside you don't see any magnetization, as Professor Ding mentioned. Okay, so it's very difficult. There are strong repulsion forces between these pieces, and when you install the first piece, it's easy, but when you install the last piece, you encounter a tremendous repulsive force. So the installation is not easy, not trivial, and we have to prove to NASA that it's safe in space, even when the glue degraded through radiation. So we have to build 3 magnets, and one is built to destroy okay, just to prove it's safe. In AMS 02, the Chinese Academy participated in the design and manufacturing of the calorimeter we just saw. Shandong University, they collaborated with our National Space Organization, and they participated in the design and manufacturing of the thermal control system. Okay. And Shanghai Jiao Tong University is responsible for the cryogenic ground support equipment, which is needed to operate the cryomagnet on the ground before launch. Shanghai University, they collaborate with our Military Research Institute and AITC among many other institutes in the design and manufacturing of the tracker thermal control system, which is required to bring the heat generated by tracker inside the superconducting magnet and bring it outside and radiate into space. Taiwan collaborates closely with MIT in the design and production of the electronic system of the AMS detector. We have 7 gigabits of data generated from about 300,000 sensors. You just heard the talk. However, we can bring down the data from space station to Earth. The bandwidth is only 2 megabits per second. So we have to reduce the data from 7 gigabits per second to 2 megabits per second, online. So we need very fast processors. There were no such commercially available space components for us. So we need to design and build this based on technology developed in accelerator-based experiments. We adapt it and make it useful in space. Okay. Also, for space application, reliability is very important. So we have to build fourfold redundancy into this electronics. And aside from the redundancy, we also need very stringent qualification procedure. So we have to build at least 2 versions of qualification modules. That's why we have to build about 800 modules, even though only about a quarter of them are put into space. So these are the flight modules, flight crates assembled on the integration jig at CERN. They come with all the documents, qualification documents associated with each piece of the equipment. Both China and Taiwan also contribute to the cryomagnet system, and we contribute to power distribution system. And as I mentioned, we also participating in the thermal design and manufacturing. So these are examples of the thermal system. A large fraction of thermal control system was built in Taiwan at AITC. We have these 3 by 3 meters main radiators. We have tracker radiators, and we have a various piece of tracker thermal control system. Remember that we bring 2,500 liters of superfree helium, which is at temperature 272 degrees below zero, which is even cooler than the universe. And we generated about 3 kilowatts of heat. About 150 watts were inside the superconducting magnet generated by the tracker. And to bring this heat outside and dissipate into space, in space you don't have air, you cannot use fan. So this is non-trivial. And so this is one of our major contributions to AMS as well. So in order to do all of this, we have to procure equipment just for this experiment. For example, the National Space Organization has to procure this thermal vacuum chamber for test of electronics, and just for AMS. In each university in mainland China, there is an AMS Science Center established. Okay, so this is the one at Shanghai University at Guangzhou. Okay, so most of these are supported by local governments of China. International collaboration is an important element of this project. Scientists from 15 countries come to Taiwan every 3 months for the technical exchange meeting on electronics. And they also come to work with local scientists to test and qualify each piece of electronics equipment produced. Of course, scientists from China and Taiwan also go to US and Europe to collaborate with our AMS partners. And some of my colleagues, they always regard international collaboration as an obligation, and I have to remind them to consider international partners as part of our resources. We learn and grow through this project. In conclusion, after 15 years of efforts, not only scientists are eager to see the great science to come out of this experiment, the funding agencies are even more eager to see us on the space station. Okay. They took on great responsibilities to support us through the difficult periods, right, of the shuttle accident, and when NASA removed us from the shuttle manifest. So they really will feel relieved to see us on the space station, and hope that we will not go back to ask for more support. Thank you very much.
Good evening. I am the last speaker, and I have good news for you. I only have 6 transparencies. And I'm going to go fast. This is, I guess, my presentation is a good example of the management of Professor Ting to join enormous groups with small groups and have everyone contributing at their own scale. I apologize for the order in the flags, but it was the ordering was actually taken from a transparency by Professor Ting. You may recognize actually the lettering. So it's not. I apologize for the colleagues from other countries. I will describe to you a contribution from my university. Everybody has been naming here countries, so I would say Mexico because I identify Mexico with our university. It's a small contribution because our country is comparable in economically smaller, but you will see that I will describe very briefly what we have done. The equipment has been described to you in more than one talk today, so you see the equipment here. We have collaborated very closely with the French colleagues in Grenoble, and they were as part of the construction of the REACH detector. This is the ring imaging, the CHerenkov detector, the ring imaging CHerenkov detector is actually there. I just repeat, to measure both the velocity and the charge of the particles, and to ensure a good resolution in the velocity and in the charge of the particles. There are certain secrets that you have to do, and I will describe some of the details, which is what we have been doing right now. So I am repeating here some of the figures you have seen before. I just put here just to give you the scale of the Mexican economic contribution to this thing, which is very small. We paid for some 1/8 of the aerogel, which are right now on the current version of the detector, and we paid for just a symbolic part of the photomultipliers, just to make sure that our country is there. Now, in order to have good resolution in the charge detection, what you need to do is to increment as much as possible the number of photons that are produced by each particle going through. The number of photons is proportional to the charge square, as it was mentioned by Professor Aguilar, but it's also dependent on the optical properties of the radiator. The radiator is this piece it's a gel made out of silica, and this gel is very light and it has very little density, and the optical properties of this material had not been measured before with such detail. So we were charged with characterizing this material, and it turns out that the Cerenkov angle is dependent on what is called the refractive index of the material, which happens to be a function of the color of the light. So we had to, in order to measure this dependence, which is called the dispersion law, we went and shined lasers of different colors through a sample of through samples of this material, and by so doing, we were able to get the parameters for this dispersion law, and also we proved that this material scales so that with the density. So if you have higher density, you just get more. You get a different amount of the refraction index scales linearly with that. This allowed us to evaluate other properties of which are important for the detector, like what is called the chromatic dispersion, which I don't have the time to explain to you very much. This we did in our institute. This was done in a somewhat primitive way. I mean, we set up with our optics equipment there. There you have one of the aerogel samples. So you shine a laser through it and see how it diffracts the light, and you go and measure someplace far away, because these things have a very small refractive angle. And so we actually, in order to get the position where the light shines, we put a screen and a CCD to locate well the point. And so we were able to get for a number of samples provided by the manufacturer, we were able to see how well these manufacturers, what was the uniformity in the diffractive angle for all the samples. It turns out that they are fairly uniform, but within within of the order of a percent, you see important variations. These aerogels are actually like jelly, and they are cooked basically, and so it depends on how they are cooked. They could vary a little bit. So the first thing we did was, as I said, to find what was the quality control of the manufacturer. And then we also found that the actual dimension of the samples were not uniform. They varied a little bit from one to the other. So once we found out that, it was quite clear that it was necessary to characterize, if you want to have good resolution for all the charges, you have to characterize all the 100 tiles and have a measurement of about 100 measurements on each tile of these properties, and have this as a table someplace, which is for the calibration to get the good charge resolution. This was done not in Mexico, but it was done with some Mexicans with the help of Mexicans in France. There was a student who spent there like 2 or 3 years building with Professor Bonner in France an automated method in which what we had done by hand, it was done with the remote control, computerized and everything. So for every tile, the refractive index was mapped, and also the thickness variation was mapped, and it was all collected in a table, which is now part of the calibration of the whole ridge detector. One other problem that was assigned to us to solve, well, not to us, everybody was mentioned in the collaboration that during the first flight, the aerogel seemed to have aged. When it came back, it had lost a little bit of its transparency, and people wanted to know if that was a problem and how to tackle it. So we set up. Some people were saying that the aerogels could have suffered from the thermal cycle of the shuttle going around and warming and cooling and so on. So we set up a small thermal cycle device in our laboratory at vacuum. And what we found out is that, later on, what I'm going to say sounds trivial, but this aerogel is like sponge. So somehow what happens is that if you vacuum, put this thing under vacuum and then admit air into it, when you do the process of admitting air into it, if this air is not clean, then it just sucks dirt and it loses its color. And I'm not going to describe all the details, but we actually did that by having a dirty vacuum pump and a very clean vacuum pump, and seeing that when you do the things very properly, then the thing doesn't lose its transparency. So provisions have been taken in the current version to isolate the detector from this type of problems. So this is my last transparency, and this just presents the group here. And I didn't thank you for being here. There is a long tradition of Mexican UNAM collaboration with RISE. I used to run experiments with this fellow here at the Bonner Lab a long time ago, and now we have one of your accelerators in Mexico. Few of you may remember that once you had a tandem and a single-ended Van de Graaff, which is now in my institute. Thank you very much.
Thank you so much, and welcome back to Rice. Isn't this an amazing story? I hope that you all will, as many as possible, attend the launch and follow the launch. We'll try to be sure that we are able to follow the science and make information available to you. I've consulted with my colleague, Dr. Ting, and we think we won't take the time for formal questions. I started this a bit late, and there's much to talk about. If this looks hard, it is hard. It's a measure not only of the challenge of the science, physics, astrophysics, but the management and organization of such an extraordinary effort. So my congratulations to everyone. My thanks to Sam Ting, all his colleagues who traveled a long way to be with us, to the crew. We greatly appreciate you taking this experiment up. And we will stay a few minutes so that if some of you would like to come and meet our colleagues, we welcome you. And Congressman, thank you very much for being with us as well. Thank you.